So what we're going to be talking about today is kind of like a complicated module. It's called navigation. So if you ask me, this is probably the most important module in the field of robotics. So when you look at like jobs in at self-driving car companies, right? They will almost always want somebody who's an expert in navigation or motion planning. So if you ask me, this is like the top skill to have in the field of robotics: navigation, machine learning, and control theory. So with that out of the way, although this will be sort of complicated, I did feel that this was necessary for me to talk. So yeah, let's get started with this lesson. Not only is navigation a little bit complicated as a subject, but it also involves all of the stuff that we have done in the previous lessons. So you will see some sort of implementation of a line following sensor in your complete navigation package. And your line following sensor, if you remember, it also, draws upon the previous modules that we have, like reading from sensors, making robots move through kinematics. So all in all, navigation is like your total complete package that a robot, basically any autonomous robot should have. Yeah, so that's what I'll be talking about in this lesson. So next week's lesson will sort of be I'll sort of cover the stuff that I have missed out on previous lessons. So I know that in last week's lesson, Aditya and I think it was Alan, they both wanted me to cover a bit more on control theory and maybe like reinforcement learning or something like that. So I'll include those things in lesson 6, that is next week. But for now, I'll just entirely be focusing on what navigation is all about. Okay, so before we go any further, I just wanted to ask you guys a question. So based on this video, what do you think navigation is? So it does involve path planning. That in fact, path planning is perhaps the hugest part of navigation, but it also involves something else. It also involves following a specified path, but it also involves stuff like obstacle avoidance. You can see here that the path that this robot is generating, right? It sort of generates a path that does not go over the cones. So there is some sort of implicit obstacle avoidance also taking place. Anyway, I just wanted to get your understanding of what the subject is. I'll go over them formally in a bit. So yeah, so I'll be going over what navigation is, why it's important, what are the different constituent components of navigation. Then I'll also be doing a small demonstration on obstacle avoidance in VREP. And I'll have you guys sort of like, especially if you guys are those of you who are undergrads, I'll have you guys code up one particular type of algorithm in trajectory planning or path planning. And yeah, that's what we'll be doing in today's lesson. So navigation basically means how can I move from point A to point B, or from my source where I'm currently located to a destination point without hitting obstacles, and doing so in the most efficient possible manner. All right. So you would not want to, have a generated path that is very long or very energy consuming. You would want to have a path that is that avoids obstacles, but also finds a shortest distance, shortest path between A and B. So all of the tasks that, all of the subtasks that involve these two things, right? Those are what you can call navigation tasks. So in this particular video, I think this was a challenge given by the US military. I think it was a DARPA challenge. So you can see that a UAV is going down an underground mine. So you can see that while it is traveling, it is following a line, like Alan said, and it is also generating a path for itself. So rather, it generates a path first, and then it follows that path. So, and it does so without hitting the walls or hitting any obstacles. So that's essentially what navigation is all about. Yeah. So in more formal terms, all these things that you see here, all these blocks that you see here, they are essentially what constitute navigation. So you have your localization. So that basically answers the question, okay, where is the robot in its environment? Where am I? Then it also then you also have mapping. So knowing where the robot is not enough, right? You need to know where the obstacles are in the environment. Otherwise, there would be no use just having a robot that knows where it is and doesn't know where its obstacles are. So localization and mapping are sort of interlinked. I'll get to that in a bit. So they're usually a couple problem. So when you talk of localization, you also usually talk about mapping. Okay. So those are the first two components of navigation. Then you have obstacle avoidance. All right. So knowing where the robot is, knowing where the environment is, it's not enough. Okay. You need to actively avoid obstacles in your way. So that's what obstacle avoidance is about. So we'll also do a small VREP demo on just obstacle avoidance. So obstacle avoidance is kind of it's pretty simple. There's not much to it. But the real beast comes in trajectory planning. So this has many names to it. As Aditya said, Aditya mentioned path planning. So path planning is just another term for trajectory planning. So knowing where your robot is, knowing where the environment is, how do I generate a path from your source to your destination? That generation of a path is what is covered under trajectory planning. So usually obstacle avoidance is integrated in trajectory planning, and this is by far the most complicated module of navigation. So just wanted to let you know that usually obstacle avoidance goes hand in hand with trajectory planning. Okay, so now we've generated the path, but how do we enforce the robot to follow along that path? So that's what Alan mentioned, right? Like following a specific line or something. So that's where motion planning comes in. So once you've generated a path between A and B, how do you force your robot to follow along that path? So that's the whole science behind motion planning. And if you recall from our previous lesson, we have already done this. So the line following the robot that you made last week. So yeah, so that's basically motion planning, because you had a path laid out for you, right? We created a path in VREP, and you just had to create a control strategy that forced the robot to follow along that path. So that's essentially motion planning. So that's something that we did last week. Yeah. And kinematics and control, they come inside motion planning. So now I hope you can get a sort of big picture overview as to the scope of autonomous robots. So the task of navigation is like, say, you can say the most basic task of what an autonomous robot should do, and it contains all of these things. So any questions so far? So in today's lesson, I'll briefly touch on all of these things, but your demonstration on VREP will be on this, and your programming assignment will be on this trajectory planning. Yeah. Okay, so localization, that is the first step in the whole navigation scheme. So we've actually covered this in lesson 3, if you recall. So the whole question of localization basically means, okay, where am I? Where is the robot located? So you can give basically 2 answers to this. You can give a global frame answer, or you can give a local frame answer. So your global frame answer is just your GPS reading. That's fine, but in most practical applications, you cannot just rely on your GPS. For example, your mining application right here, right? your GPS won't work under the ground or under the surface. So you'll have to rely on other sensors. And we sort of talked about these other sensors. You have your odometry or your encoder, and you have your inertial measurement unit, which basically measures your acceleration. So now keep in mind, both of these are prone to errors. These sensors are very noisy. So they cannot give you a perfect picture as to where you are. They can only give you an approximation. And I'll touch upon this a little bit more in the next slide. Okay, so now with localization, you know where your robot is in an arbitrary local frame in the environment. But you need to know where the obstacles are located, right? So that you can make a trajectory that avoids the obstacles. So that's where mapping comes in. So mapping is basically the task of figuring out your entire environment, where the obstacles are, where the people are, in case it's a dynamic environment. And yeah, so that's the task of mapping. So there are broadly two ways you can do mapping. So one is you can sort of manually feed in the data of where the obstacles are in the environment. So that sort of works in a static environment. So suppose you're, I don't know, suppose you have a Roomba. Roomba is a bad example, but suppose you have like a warehouse, and you sort of, and where things are located in the warehouse is relatively fixed. Like all the shelves, all the, machinery, they'll all be located in certain areas. So you can just tell the robot, you can basically feed the robot that, hey, the obstacles are located here, and whatever planning you do should actively avoid those things. So that's option B that you see here, feeding a map to the environment of the environment to the robot. So that actually works well in static environments, but in real life scenarios, you won't have a static environment. You'll have a dynamic environment. Your environment will always be changing. So in that case, what you have to do is you have to use your sensors to constantly tell you, okay, these are where the obstacles are at this given time frame. So in fact, if you see here, yeah. So that is what this robot is doing. You can see that as it progresses, its sensors sort of pick up where these cones are. So this is sort of doing a mapping process on the fly or instantaneously. So this is also a good time to bring up the question that Alan initially mentioned. So will your line sensors be able to, will your IR sensors be able to pick up information on the environment if it's a fast car, if your car is going fast? So yes, real life robots should be able to, real life robots and sensors should be able to pick up that information regardless of what speed you're going at. Maybe with the small boards that you're using, there could be a discrepancy, but professional grade sensors and computers should be able to easily adjust for that fact. Okay, so that is option A. Using the sensors to give you like a real-time information of the surroundings, and that is usually what is done in actual robotics. So think of localization and mapping as a sort of an example where a person enters a dark room that he has no knowledge about. So he only has a flashlight and he enters a dark unknown room. So he basically has to figure out, okay, these are where certain landmarks are, like say the door is to his right, or say the refrigerator is on his left, or something like that. So he has to figure out as he explores the room where things are, and that's exactly what robots do in unknown environments. Like a self-driving car does not have a map that map of the world, right? Because things keep changing, cars keep going and moving around, people keep moving and coming in and going. So the field of SLAM, simultaneous localization and mapping, so that is what this whole topic is about. So We've actually even talked about this in our third lesson. Uh, this uses Kalman filters, so I just left a link for those interested. But this is an active area of research in robotics.